Welcome in. Today is Friday, March 6th, 2026, and we are just thrilled to have you joining us for today's deep dive. I want to start by having you run a quick, mental inventory of your immediate surroundings.
That was a good exercise.
Yeah. Think about the smart zone sitting right there on your desk, or maybe it's in your hand. Consider the solar panels you might see on a neighbor's roof across the street, or even the battery architecture inside that new electric vehicle parked in the driveway. It is incredibly easy to look at those disparate technologies and just see them as completely separate marvels of modern engineering.
Right, they feel unrelated.
Exactly.
Yeah.
But what if there is an invisible thread connecting every single one of them? What if the underlying architecture of the modern world relies on a singular, hidden material to actually function?
It is a truly profound realization. When we look at the infrastructure of the 21st century, the ultimate bottleneck isn't necessarily software or processing logic. It actually comes down to physical materials.
Physical constraints.
Yes. And the specific material we are talking about today is something most people probably associate more with historical currency, an antique heirloom, or a piece of jewelry than with the bleeding edge of artificial intelligence and the green energy transition.
That disconnect is exactly why we're doing this deep dive. Our mission today is to completely reframe how you think about element 47 on the periodic table. Silver. We are taking a massive stack of research ranging from technical university chemistry data and historical encyclopedias to comprehensive industrial guides and the brand new February 2026 market reports to uncover how this ancient currency became the irreplaceable engine of modern civilization.
It's quite the journey.
It really is. We're going to explore a journey that takes a material from the ancient world straight to the futuristic circuits that power our lives today.
And that journey is currently colliding with a rather harsh economic reality. As we will explore later on, we are facing a massive global supply deficit. The mining of silver is incredibly inelastic, which is creating a perfect storm in the markets right now. But before we can really understand the macroeconomics of global supply chains, we have to understand the physical material itself. We have to look at why this specific element behaves the way it does.
Okay, let's unpack this. We have to start with the elemental marvel that is silver. Let's look at the timeline first. Humans have been pulling this metal out of the ground for a staggering amount of time. I mean, well before the advent of complex industrial machinery. We are looking at a relationship that goes back thousands of years.
That's right. The organized mining of silver dates back to around 3000 BC, primarily emerging in regions like Anatolia, which is modern-day Turkey.
So 5,000 years.
It is a profound 5,000-year relationship. On the periodic table, it sits at atomic number 47. It's designated by the symbol Ag, which originates from the Latin word argentum.
And scientifically speaking, it's classified as a transition metal. When we look at its physical properties, how does it compare to the other metals we interact with daily? Because I know its density is listed at 10.5 grams per cubic centimeter, but what does that actually feel like in a practical sense?
Well, to put that 10.5 grams per cubic centimeter into perspective, it means silver is significantly denser than iron or steel, but it is noticeably lighter than gold or lead.
Okay.
If you were to hold a solid block of silver in one hand and an identically sized block of iron in the other, the silver would feel substantially heavier. It also boasts a relatively high melting point of 1235 Kelvin.
Which translates to what in terms of normal temperatures?
That translates to roughly 961 degrees Celsius
Yeah.
or 1763 degrees Fahrenheit.
That's incredibly hot.
It is. And this specific thermal threshold is crucial for industrial applications because it means silver can withstand immense heat without losing its structural integrity, yet it can still be melted down and refined using traditional high-temperature furnaces.
But the density and the melting point aren't what gives silver its real power. The research emphasizes that the true superpower of silver, the reason it fundamentally runs our modern world, comes down to its microscopic architecture, specifically its electron configuration.
The quantum level?
Right. The technical designation for its ground state is a krypton core, followed by 4d10 5s1. Now, for those of us trying to visualize this at the atomic level, what does a krypton core actually mean? And why does that sequence dictate the metal's behavior?
What's fascinating here is how the atom is constructed from the inside out. When we say it has a krypton core, it means the inner 36 electrons of a silver atom are arranged in the exact same highly stable, tightly packed configuration as the noble gas krypton.
So they are secure.
Very secure. Those inner electrons are locked in, they are perfectly balanced, and fiercely hold on to the nucleus. Because they are so tightly bound, they create a powerful shielding effect.
So they essentially block the magnetic pull of the nucleus from reaching the outer layers.
Precisely. Moving outward, we hit that 4d10 subshell, which contains 10 electrons. In silver, that subshell is completely full and highly stable, but then we reach the very edge of the atom. That's the 5s1 part of the configuration.
Just one lonely electron out there.
Exactly. That represents a single, solitary electron sitting in the outermost shell. Because of the massive shielding effect from the krypton core in that full 4010 subshell, the nucleus has a very weak grip on this singular 5s electron.
Which means that one electron is incredibly mobile. It's essentially free to detach and move around.
Yes. In transition metals, electrons can sometimes move between the outer shells, but silver's configuration is uniquely primed for movement. That single 5s electron moves incredibly freely from atom to atom within a solid piece of silver. And since electricity is fundamentally the flow of electrons, this absolute freedom of movement means silver provides the path of least resistance. That is why silver is the ultimate conductor of both heat and electricity. It outcompetes copper, it outcompetes gold. Nothing else on the periodic table beats it.
That structural reality perfectly explains why we use it in high-end electronics. But there's an interesting dichotomy here. The same pure state that makes it the ultimate conductor makes it physically impractical for a lot of the ways humans historically used it. If you look at a piece of silver jewelry or antique silverware, it is almost certainly not pure silver. Pure, unalloyed silver, which is denoted as 0.999 silver, is famously soft.
It is incredibly malleable. If you were to fashion a ring out of pure 0.999 silver, the structural integrity would be highly compromised.
You could just bend it.
Easily. The simple mechanical force of gripping a heavy suitcase or squeezing a steering wheel would bend the metal outer shape. The atomic layers simply slide past each other too easily without other elements to lock them into place.
So metallurgists had to solve that problem through trial and error over centuries, creating alloys. They started mixing silver with other metals, predominantly copper, to give it structural rigidity. And that history is literally stamped onto the metal today. You can read the purity based on the hallmarks.
Exactly. The hallmarks tell a precise metallurgical story. For high-end applications, you might see a stamp of 0.950, which signifies Britannia silver.
Okay, so that's 95% pure.
Right. It means the alloy is 95% pure silver and 5% copper or other trace metals. It maintains a brilliant luster and is of very high quality, but it remains slightly softer than what became the global standard.
Which brings us to sterling silver. That is the benchmark most people recognize, marked as 0.925, so 92.5% silver and 7.5% copper. And then stepping down a tier, you have what's known as European or continental silver, marked at 0.800, dropping the purity to just 80%. It is striking how introducing just 7.5% copper completely alters the physical durability of the element, locking those atomic layers in place so you can actually forge durable tools and currency.
It fundamentally changes the mechanical properties, but we have to recognize that altering the chemistry by adding copper also alters how the metal interacts with the environment. It introduces vulnerabilities, the most common being tarnishing.
This is a massive misconception. People often assume that tarnishing is an oxidative process, similar to iron.
Like rusting.
Right, but pure silver is actually highly stable. If you submerge pure silver in water or expose it to oxygen, it doesn't break down or degrade the way iron does. Pure silver doesn't rust. The black degradation that we call tarnish only occurs when silver meets one highly specific atmospheric compound.
Yes, the chemical culprit is hydrogen sulfide. When silver interacts with the trace amounts of hydrogen sulfide in the air, a chemical reaction occurs that forms silver sulfide on the surface.
And that's the black stuff.
That silver sulfide is the black layer of tarnish. So it isn't the ambient oxygen destroying the surface of a silver coin, it is the minute presence of sulfur compounds in the environment.
Beyond its interaction with the air, the university safety data outline some incredibly bizarre quirks regarding how silver interacts with biological systems and other chemicals. It's not a benign, inert material. The data classifies silver compounds as powerful oxidizing agents, existing predominantly in a +1 oxidation state and occasionally a +2 state.
This oxidative potential leads to some highly unusual biological interactions. For instance, while silver in its solid metallic form is perfectly safe to handle, prolonged ingestion or exposure to certain silver compounds leads to a permanent condition known as argyria.
This is the condition where human skin literally turns blue, or a bluish gray. It happens when silver particles accumulate in the body's tissues and are then exposed to sunlight, similar to how photographic film develops. Now, the documentation is clear that this isn't generally a fatal toxicity for humans. People often consume colloidal silver as a homeopathic remedy, and while it is mostly harmless to ingest in highly regulated normal amounts, the data also notes it is medically ineffective in that form. However, what is relatively harmless to human biology is devastating to other ecosystems.
The environmental toxicity data is stark. Silver is exceptionally toxic to aquatic life, particularly fish.
Really, just water exposure.
Yes. The introduction of silver ions into a waterway interferes with the osmoregulatory functions of fish gills. This means industrial byproducts, photographic chemicals, or improperly disposed silver oxide batteries pose a severe environmental hazard. They must be handled with extreme care to prevent aquatic contamination.
And it isn't just an environmental hazard. It presents acute laboratory dangers as well. The SACE protocols highlight severe volatility when silver is introduced to specific substances. If you store silver near ammonia, acetylene, or strong acids like nitric acid, it can trigger the formation of silver salts.
And those are dangerous.
Right. These aren't just unstable, they are highly explosive.
It is a profound reminder of the element's reactive potential. You are dealing with a material that possesses a hypermobile electron, allowing it to form incredibly strong bonds, but also allowing it to react violently when placed in the wrong chemical environment. It demands strict handling protocols.
So we are looking at an element that is soft in its pure form, highly conductive, vulnerable to sulfur, toxic to aquatic ecosystems, and potentially explosive under the wrong conditions. How does a metal with this specific quirky profile become the absolute backbone of the modern digital age? Let's transition into the hidden presence of silver in our daily lives. Let's look at the electronics sector.
The sheer scale of industrial consumption is staggering. If we look at the verified data for 2024, industrial applications consumed 680 million ounces of silver.
680 million, that's massive.
It represents 59% of the total global demand for the entire year. To understand the velocity of this shift just a decade ago, industrial applications represented a significantly smaller fraction of total use. The demand profile has fundamentally inverted.
And the lion's share of that industrial demand is driven by the devices we rely on constantly. The 2023 figures show that the electronics sector alone consumed 445 million ounces. I think it's helpful to break that macroscopic number down into the actual hardware sitting in our homes. There is no alternative material used in these circuits. That smartphone we talked about earlier, it contains between 200 and 300 milligrams of silver.
Per phone.
Right. A standard laptop houses roughly 750 milligrams. If you look at a modern flat-screen television, you're looking at 1 to 2 grams. And high-performance gaming consoles require 2 to 3 grams just to manage the advanced graphics processing and thermal loads.
When you take those individual milligrams and gram counts and multiply them by the billions of consumer devices manufactured globally every single year, you begin to visualize the immense physical draw on global silver reserves. But consumer electronics are only the baseline. We are currently entering a massive, unprecedented wave of new demand driven by enterprise-level infrastructure, specifically data centers, and the explosion of artificial intelligence.
AI is incredibly resource-intensive. We're talking about workloads that require unprecedented computational power, and a direct byproduct of that massive processing power is heat. Extreme hardware melting heat.
This is where silver's unique dual capability becomes non-negotiable. Because it is the absolute best conductor of both electricity and heat, it is integrated into the core architecture of these AI server farms. It ensures the fastest possible data transmission with minimal power loss across circuits and microconnectors.
So it moves the data fast.
Very fast. But more importantly, silver-based thermal interface materials are utilized to efficiently draw the massive heat loads away from the processors.
Without it, those high-end AI chips would literally overheat and fail. By maximizing thermal transfer, silver significantly reduces the massive energy demands required to artificially cool these sprawling data centers. It is an efficiency multiplier. And the supply chain feeding this technology is highly centralized and incredibly predictable.
Yes, the geographic concentration of manufacturing creates intense seasonal pressures on the silver market. The 2025 industrial guidance reports that China produces over 70% of global electronics. This centralization creates highly predictable, massive demand spikes in the global silver market.
The rhythm of the global tech industry dictates the flow of the metal. During the second and third quarters of the year, manufacturers began aggressively ramping up production ahead of the global holiday shopping season. They have to secure and take physical delivery of millions of ounces of silver in a very tight window.
The logistics are staggering.
The spot price and physical availability of an ancient element literally fluctuate based on the modern holiday gadget rush. It's wild to think about.
It is a fascinating tether between geological constraints and consumer behavior. But the tech industry isn't just focused on producing higher volumes of devices. The engineering imperative is miniaturization. The goal is constantly to build smaller, more efficient architectures.
Here's where it gets really interesting. The research outlines a jaw-dropping breakthrough regarding this exact push for miniaturization. We are looking at the development of the atom-thick switch.
This is a remarkable piece of engineering.
Scientists at the Institute of Science Tokyo have essentially achieved a level of microengineering that challenges the physical limits of materials. They have built a silver-based mechanical switch that operates at the thickness of a single molecule.
The mechanics of this molecular switch are truly profound. The research team constructed this device on a microscopic insulating layer of tantalum oxide. The breakthrough revolves around how silver atoms migrate when subjected to an electrical current.
They literally move the atoms.
Yes. When the engineers apply an incredibly tiny voltage, specifically just 1/3 of a volt, the silver atoms physically move through the tantalum oxide layer. They align to form a microscopic atomic-sized filament that bridges the gap, completing the circuit. That represents the on state of the switch.
And the moment that tiny voltage is removed, the structural integrity of that tiny silver filament collapses. It breaks apart, the circuit disconnects, and the switch returns to the off state. But to achieve this level of atomic precision, they couldn't just build it in normal atmospheric conditions, right?
No, the environmental controls are critical. The researchers discovered that to stabilize these microscopic silver filaments and ensure they form and break predictably, the process must occur within an environment saturated with acetylene gas. The gas interacts with the silver atoms, providing just enough stability to make the filament functional without making it permanent.
Now, to manage expectations, the documentation notes that in its current iteration, this atomic switch only maintains its stability for fractions of a second. It is firmly in the proof of concept phase.
Right. It's not in your phone tomorrow.
Exactly.
Yeah.
But conceptually, it proves that it is physically possible to build microscopic processing chips that can carry an electrical current stably and safely, utilizing only a fraction of traditional electricity, and thereby producing minimal heat. It completely redefines the boundaries of computing architecture.
If we connect this to the bigger picture, it dismantles the assumption that as technology becomes more advanced and miniaturized, we will somehow require fewer physical resources. In reality, our reliance on the unique quantum properties of silver only deepens as we push toward the atomic scale. The precision requires the absolute best material available.
Which perfectly bridges us to what is perhaps the most aggressive driver of silver demand on the planet right now, the transition away from fossil fuels. Let's look closely at the green energy sector, focusing specifically on solar power and electric vehicles. The consumption figures for solar photovoltaics, or PV, are escalating at a rate that almost defies the traditional mining supply curve.
The year-over-year growth is staggering. In 2022, the global solar industry consumed 118.1 million ounces of silver. By 2024, that figure had skyrocketed to 197 million ounces.
Wow.
That represents a 64% increase in consumption in merely 24 months. As we sit here today, nearly 1/5 of the entire global demand for silver is entirely consumed by the manufacturing of solar panels.
To truly grasp why solar power is so devastatingly reliant on this metal, we need to break down the anatomy of a solar panel. How does sunlight actually become usable electricity, and where exactly does the silver fit in?
The process relies entirely on silver's unmatched electrical conductivity. A standard residential or commercial solar panel requires roughly 20 grams of silver. During the manufacturing process, this silver is finely ground into a microscopic powder and formulated into a highly conductive paste.
Like an ink.
Very similar to a thick ink. This paste is then meticulously screen printed in micro-thin lines across the surface of the silicon wafers.
So the silicon is the material that actually interacts with the sunlight.
Correct. When photons from sunlight strike the silicon wafer, the energy knocks electrons loose from the silicon atoms. But loose electrons don't generate power unless they are collected and directed into a current.
And that's where the paste comes in.
Because silver provides the ultimate path of least resistance, those micro-thin printed lines act as a highly efficient superhighway. They instantly capture those freed electrons and transport them out of the panel with virtually zero resistance or power loss, allowing the current to be directed into the grid or stored in a battery.
With silver prices climbing, It is obvious that solar manufacturers are desperate to protect their profit margins. The 2026 World Silver Survey dedicates significant analysis to an industry-wide trend referred to as thrifting. This is the concerted engineering effort to replace silver with cheaper, more abundant conductive metals, specifically copper or aluminum. But the report confirms that these thrifting efforts are fundamentally failing. Why can't we just use copper paste instead of silver paste?
It comes down to the physical limitations of the substitute metals. When engineers attempt to screen print copper or aluminum into the ultra-micro thin lines required for highly efficient modern solar panels, the substitute metals simply cannot match the conductivity of silver. At that microscopic scale, the electrical resistance of copper and aluminum becomes too high.
The electrons effectively hit a traffic jam.
Exactly. The resistance generates heat, the flow of electrons slows down, and the overall efficiency of the solar panel plummets. If a panel is less efficient, you need more panels to generate the same amount of power, which entirely defeats the economic purpose of using a cheaper metal. For the high-efficiency panels driving the green transition, silver is structurally irreplaceable.
And that technological bottleneck leads to an economic and geological projection that is genuinely terrifying. The researchers at the University of New South Wales modeled the trajectory of this demand. They concluded that if current, sustained growth rates in global solar panel production continue, the solar manufacturing sector alone could consume between 85% and 98% of all currently known available global silver reserves by the year 2050.
The magnitude of that projection cannot be overstated. We are looking at a single technological application potentially exhausting the global reserves of a foundational element within a quarter of a century.
I have to push back on that slightly, though. Surely those models are factoring in an end-of-life recycling. If we are deploying hundreds of millions of panels, we will eventually recycle them and reclaim the silver, mitigating that 98% depletion rate.
The models do account for recycling, and that is what makes the math so alarming. Even if the industry achieves a highly optimistic 85% recycling rate for decommissioned panels, which requires massive advancements in chemical extraction, given how difficult it is to separate the silver paste from the silicon and glass, the structural deficit remains massive.
Because we're building so many new ones?
Precisely. The sheer volume of new capacity required to meet global energy transition goals vastly outpaces the trickle of secondary silver entering the market from recycled panels.
So even in a best-case recycling scenario, the green energy transition is on a collision course with geological scarcity, and solar is only half of the equation. The automotive sector's shift toward electric vehicles is compounding the crisis. Let's compare the raw material requirements. A traditional internal combustion engine vehicle, a standard gas-powered car, utilizes roughly 15 to 28 grams of silver. That covers the various electronic switches, the infotainment system, and the internal relays. What happens when you transition that architecture to an electric vehicle?
The consumption profile essentially doubles. A standard electric vehicle requires between 25 and 50 grams of silver.
Just for one car.
For one car. This increase is driven by the complex power management systems, the advanced battery management architecture, and the high voltage connections required to move electricity from the battery to the drivetrain efficiently.
And that 50 grams only accounts for the vehicle itself. The infrastructure required to keep that vehicle moving is vastly more demanding. The data reveals that constructing a single commercial-grade fast-charging station requires between 1 and 2 kilograms of silver.
That is a massive jump.
We've moved from milligrams in our smartphones to literal kilograms in our civil infrastructure. The power electronics required to safely channel grid-level electricity into a vehicle battery in a matter of minutes demand massive high-gauge silver contacts to prevent catastrophic heat buildup.
Furthermore, we have to look at the future trajectory of battery technology. The industry is aggressively pursuing the development of solid-state batteries, which offer higher energy density and faster charging times. However, if solid-state batteries reach commercial scale, the silver requirements could increase exponentially.
How exponentially?
Current engineering models suggest a standard 100 kilowatt-hour solid-state battery pack might necessitate an astonishing 1 kilogram of silver per vehicle.
The sheer volume of material required to execute this global transition is unprecedented in human history. We're rebuilding the global energy grid and transportation network on the back of an element that is becoming increasingly scarce. But silver's utility isn't confined to energy generation. We need to explore our fourth area of focus: how the specific properties of silver are revolutionizing medicine, dramatically improving battery safety, and even being utilized to control atmospheric weather patterns.
Let's begin with battery safety, as it perfectly illustrates how nanoscale material science can solve massive, real-world consumer issues. We are all familiar with the degradation of lithium-ion batteries. Whether it's the battery in your smartphone losing its charge capacity over a couple of years or an EV battery failing, the underlying cause is often structural degradation.
Right. When you rapidly charge a lithium-ion battery or subject it to repeated thermal stress, the solid ceramic electrolytes inside the battery begin to fail. They develop microscopic fissures and cracks. Once those cracks form, the lithium begins to intrude into them, widening the fractures and eventually leading to a complete failure of the battery cell.
To understand the solution to this, we must examine the breakthrough research conducted at Stanford University, led by Associate Professor Wendy Gunn. Her team approached the problem from a deeply pragmatic angle. They recognized that manufacturing a mathematically flawless, uncrackable ceramic electrolyte was physically impossible and economically unviable, so they focused on mitigating the damage.
She uses a brilliant analogy to explain their approach. She suggests looking at these solid electrolytes like a ceramic bowl you might use in your kitchen. Over time, with constant use, heating and washing, the surface of that ceramic bowl inevitably develops tiny, microscopic hairline cracks. You can't alter the fundamental nature of the ceramic to stop it from aging, but you can apply a protective glaze to the surface to prevent those hairline fractures from deepening and shattering the bowl.
That is exactly the principle they applied at the nanoscale. The Stanford research team discovered that if they coat the surface of the solid ceramic electrolytes with an impossibly thin layer of silver, it profoundly alters the structural longevity of the battery. We are talking about a coating just 3 nanometers thick.
3 nanometers is almost incomprehensibly thin.
It is, but the crucial innovation was that they didn't use standard, neutrally charged metallic silver. They utilized silver that had been stripped of an electron, rendering the silver ions positively charged.
How exactly do you apply a 3 nanometer layer of charged silver to a battery component?
It requires extreme precision. They deposit this positively charged silver layer while maintaining the manufacturing environment at a precise 300 degrees Celsius, which is roughly 572 degrees Fahrenheit. At this specific temperature, the silver ions bond perfectly to the ceramic surface.
And the results of this process are incredible. Because the silver layer is positively charged, it physically repels the positively charged lithium ions. It literally blocks the lithium from forcing its way into the existing microcracks, and the data shows it effectively stops new cracks from propagating. In their stress tests, the batteries treated with this 3 nanometer silver shield proved to be 5 times more resistant to cracking than untreated batteries.
It's a massive leap forward in extending the life cycle of our technology. And this isn't the only critical battery breakthrough involving silver. We also have to consider the research published by officials at the Korea Electronics Technology Institute, or KETI. Their research focused on a different mechanism of battery failure, the formation of dendrites.
Dendrites are essentially microscopic, rigid crystals. They grow organically inside the battery's solid electrolyte over time. They look almost like tiny metallic tree branches. And they are highly dangerous because if they grow long enough, they pierce the separator between the anode and cathode, causing a catastrophic short circuit which can lead to thermal runaways and fires.
Exactly. The KETI researchers proved that by integrating silver nanoparticles directly into the solid electrolyte matrix of a lithium battery, they could successfully suppress the nucleation and growth of these dendrites. The silver fundamentally alters the electrochemical environment, preventing the crystals from forming in the first place. This makes high-capacity batteries vastly safer and dramatically extends their operational lifespan.
So silver is healing the microscopic biology of our batteries. But its ability to interact with actual biology, human biology, is an entirely different, massive sector of demand. The healthcare industry is a huge consumer, utilizing roughly 30 million ounces of silver every single year. And this demand is rooted in silver's natural, potent antimicrobial properties.
The mechanism of action is fascinating. At the cellular level, silver ions possess a high affinity for the specific proteins that construct the cell membranes of bacteria.
They target the structure.
Yes. When silver encounters bacteria, it binds tightly to these structural proteins, physically degrading the cell wall, rupturing the membrane, and destroying the pathogen.
This inherent lethality to bacteria has become increasingly vital in modern medicine, particularly as we face a global crisis of antibiotic-resistant superbugs. Traditional antibiotics are failing against certain strains, But a physical attack on the cell membrane using silver ions is incredibly difficult for bacteria to evolve a defense against.
Because of this, silver is completely non-negotiable in modern infection control. It is woven into advanced wound dressings for burn victims, it is used to coat surgical instruments, and it is embedded in catheters to prevent hospital-acquired infections. The medical sector represents a highly stable, non-cyclical source of demand.
Right, it's not like consumer electronics.
Exactly. A hospital administrator cannot choose to compromise on critical infection control simply because the spot price of silver increases. They will absorb the cost to ensure patient safety.
And the medical applications are advancing far beyond simple sterilization. The diagnostic innovations are astounding. Let's look at the breakthrough from the Brazilian engineers at the University of São Paulo who collaborated with the Brazilian Agricultural Research Corporation. They engineered a flexible biosensor that costs exactly $2 to manufacture. It is literally printed onto a thin strip of polyester film, and its purpose is to analyze human saliva for a highly specific biomarker called BDNF.
BDNF stands for brain-derived neurotrophic factor. It is a vital protein responsible for the survival, development, and function of neurons in the central nervous system.
And the clinical implications of being able to track this protein easily and cheaply are massive. The literature shows that abnormally low levels of BDNF present in a patient's saliva serve as a highly accurate early warning indicator for severe neurodegenerative and psychiatric disorders. We are talking about the early detection of clinical depression, severe anxiety, schizophrenia, and bipolar disorder.
Furthermore, it serves as a real-time metric for therapeutic efficacy. If a patient is prescribed antidepressants or undergoes targeted therapy, a doctor can administer this $2 test over a series of weeks.
And see actual biological changes.
Yes. If the BDNF levels are rising, it provides empirical, biological proof that the psychiatric treatment is physically working, removing the reliance purely on subjective patient feedback.
To understand why a $2 polyester strip works so efficiently, we have to look at its engineering. The sensor utilizes a sophisticated 3-electrode design. It features a functionalized working electrode that aggressively amplifies the sensitivity to capture the BDNF protein. It is a pure carbon auxiliary electrode to safely complete the electrical circuit, and most importantly, it relies on a pure silver reference electrode. Why is silver the absolute requirement for that reference electrode?
In electrochemistry, particularly when dealing with microcurrents in miniaturized diagnostics, the system must have an unwavering baseline to compare against. It needs a reference point that does not fluctuate. Silver provides a perfectly stable, constant voltage threshold. It boasts immense conductivity while exhibiting incredibly low rates of corrosion or signal degradation when exposed to the enzymes in human saliva. This ensures the sensor's readings are clinically accurate every single time.
So we have an ancient metal providing the baseline stability for a $2 sensor that could fundamentally democratize and revolutionize personalized psychiatric medicine across the globe. It is staggering.
This raises an important question, though. We have explored how we deploy silver to manipulate molecular environments, whether it's the chemistry inside a battery or the biology inside a hospital. But the research also points to how silver is utilized to manipulate our macroenvironment. Specifically, its role in atmospheric weather modification, commonly known as cloud seeding.
Cloud seeding using silver iodide. This is a topic that carries a fair amount of public controversy, and it is important we look at the data impartially. On one side, you have agricultural advocates in drought-stricken areas and major commercial ski resorts who swear by the technology as an essential tool to save failing crops and guarantee winter snowfall. On the other side, skeptics argue that atmospheric weather is too chaotic to control, that many seeding operations fail to produce statistically significant rainfall, and that any precipitation that does occur might just be natural random chance.
To cut through the controversy, we have to look at rigorously monitored, empirical scientific studies. The sources highlight the 2017 SNOIA project conducted in the mountains of Idaho. This was a highly controlled, extensively monitored meteorological experiment designed to definitively prove or disprove the efficacy of silver iodide.
How exactly did they conduct the experiment?
The methodology involved utilizing specialized aircraft equipped with external flares. These flares burned a propane flame to vaporize and release microscopic amounts of silver iodide directly into highly specific, supercooled cloud formations.
So they flew right into the clouds.
Yes, and the researchers then tracked the atmospheric reaction using advanced radar. They literally watched in real time as snowflakes began to nucleate and grow from microscopic microns into 8-millimeter diameter crystals exclusively within the precisely seeded corridors.
And the physical yield of that experiment was staggering. The data confirms that within a 2-hour window, that specific cloud seeding operation generated enough isolated snowfall to completely fill 282 Olympic-sized swimming pools with water. That is undeniable, highly targeted precipitation.
It provided the empirical proof that the process works. However, the exact physics of how silver iodide triggers this massive freezing cascade has remained a topic of intense debate. For decades, the prevailing, somewhat simplistic theory was that silver iodide simply acted as a physical base, a solid nucleus for supercooled water droplets to crash into and freeze onto.
But recent research from the Institute of Applied Physics at TU Wien in Austria has presented a vastly more complex, nuanced theory of the atomic interaction.
Yes, the TU Wien researchers utilized nanoscale imaging to observe the process at the atomic level. They discovered that successful cloud seeding is highly dependent on the physical dimensions and structural geometry of the specific silver iodide crystals being deployed. It isn't just a matter of providing a solid surface.
It's about how the water molecules organize themselves.
Precisely. The research revealed that specific, highly structured molecular layers of water must progressively build up and stack onto the exact facets of the silver iodide crystal. The geometry of the silver iodide essentially coaxes the water molecules into aligning perfectly. Only when these specific molecular layers reach a critical threshold does the rapid freezing cascade actually begin.
Which implies that if meteorologists can perfectly synthesize the exact size and geometric surface area of the silver iodide particles they spray, they could achieve vastly more accurate, reliable, and voluminous weather modification. Once again, it all hinges on understanding and manipulating the microscopic architecture of this metal.
Which perfectly sets the stage for the massive economic reality we are currently facing. We have spent the last hour documenting an element that is structurally vital to global electronics, essential for the survival of the green energy transition, critical for next-generation battery safety, indispensable in global healthcare, and literally capable of altering the weather. Let's look at what happens when the demand for all of those applications collides with the reality of finite geology. Let's dive into Section 5, the 2026 squeeze, and analyze the current market economics and the unprecedented global supply deficit.
Welcome to the current market reality. If we look at the verified data from the February and March 2026 reports published by the Silver Institute, the market has just witnessed something historically significant. The spot price of silver has officially breached the psychological barrier of $100 per ounce.
It is a monumental threshold, and this aggressive upward price action has fundamentally recalibrated the broader precious metals market. The gold-to-silver ratio, which is the metric tracking how many ounces of silver it takes to purchase a single ounce of gold, has violently compressed, falling below 50. We have not seen that specific ratio dynamic since the massive market shifts of 2012.
The underlying fundamentals driving this price explosion are immense and multifaceted. We are operating in an environment of high geopolitical volatility and macroeconomic policy uncertainty, which naturally drives capital toward hard assets. We are seeing massive institutional and retail investor interest. The forecasts show physical investment, meaning individuals and funds aggressively purchasing physical bullion bars and minted coins, is projected to rise by 20%, hitting a 3-year high of roughly 227 million ounces.
That investment demand is competing directly with the aggressive industrial consumption from the AI and solar sectors we analyzed earlier, and this extreme competition for physical metal reveals the truly terrifying statistic for industrial manufacturers. The projected total market deficit for the year 2026 sits at 67 million ounces.
I want to make sure the gravity of that number lands. A 67 million ounce deficit means that global consumption will exceed global mining output by 67 million ounces. And this isn't an anomaly. This represents the 6th consecutive year that the global market is operating in a structural deficit. The global supply chain is only surviving by bleeding out finite, above-ground stockpiles stored in industrial vaults and commodity exchanges.
The drawdown of physical inventories is unsustainable. And what is most alarming is the supply-side response. Despite the price of the metal violently surging past $100 an ounce, the total global mine supply is only forecast to increase by a marginal 1.5%.
Now wait, I have to stop here, because this is where the traditional logic of supply and demand seems to completely break down. If an asset is hitting historic price highs, and industries are practically begging for millions of ounces to build solar panels and AI data centers, Why wouldn't the global mining industry just spin up 10 massive new silver mines tomorrow to capture those profits? It defies basic economics.
It does defy traditional economic logic, and it introduces what commodity economists refer to as the inelastic supply trap. The reason miners cannot simply ramp up production to meet surging demand is that the vast majority of the world's silver is not mined on purpose.
It's a byproduct.
Exactly. Approximately 72% of all the silver pulled out of the earth is extracted strictly as a byproduct of base metal mining. When massive multinational mining conglomerates go digging for industrial base metals, specifically copper, lead, and zinc, they naturally discover silver embedded within the exact same ore body. They extract it and sell it as a secondary revenue stream.
Which means the total global supply of new silver is fundamentally chained to the demand for unrelated industrial metals.
Precisely. If the global construction industry slows down and the demand for zinc or lead plummets, those base metal mines will reduce their operations or shut down entirely. When they shut down, the byproduct stream of silver immediately vanishes from the global market, regardless of how desperately the solar industry needs it or how high the spot price climbs.
They aren't going to mine copper just to get silver.
Right. A copper mining company is not going to invest $3 billion in 10 years into permitting and constructing a new massive open pit mine solely to extract a silver byproduct unless the core economics of the copper market completely justify the massive capital expenditure. The supply of silver is functionally disconnected from its own surging demand.
That is a terrifying structural bottleneck for the global tech supply chain. Now, obviously, there are primary silver mines out there trying to close the gap. We have major corporate players actively working to expand their output. We are looking at companies like Fresnillo, which operates heavily out of Mexico and stands as the world's largest primary silver producer. They are working alongside other massive primary producers like Peñoles, Core Mining, and Pan American Silver.
These primary producers are working aggressively. They are expanding the capacity of their existing operations, investing in deeper exploratory drilling, and attempting to commission new underground projects. However, the timeline for mining infrastructure is brutal. It can take upwards of a decade or more to navigate the environmental permitting, raise the capital, and physically construct a functioning commercial mine. They're fighting a deep structural shortage with tools that take years to deploy.
And because this element has become so exceptionally valuable, so critically scarce, and so deeply embedded in high-stakes industries, the exact origin and ethical pedigree of the metal have become paramount. Environmental, social, and governance compliance (ESG) is a massive legal requirement for tech companies. If a major tech firm is building a billion-dollar data center, they must legally prove that the silver in their servers wasn't mined using illicit or environmentally destructive practices. But tracking raw, fungible metal through the global smelting process seems impossible.
It was traditionally impossible, which brings us to one of the most futuristic and brilliant applications of technology we've seen in the supply chain space. A technology firm known as SMX, or Security Matters Public Limited Company, has successfully engineered a way to integrate blockchain tracking directly into physical raw silver.
This sounds like science fiction. How do you integrate a digital blockchain into a physical block of metal?
It requires a brilliant synthesis of physical metallurgy and advanced digital ledger technology. SMX has developed proprietary technology that allows them to embed invisible microscopic molecular markers directly into the chemical structure of the silver at the absolute earliest stage of production, right at the mine site.
I am struggling to understand the physics of this. Silver has to be aggressively refined. It gets melted down in blast furnaces at over 1200 degrees Kelvin to separate it from the copper and zinc slag. It gets poured into bullion bars, melted down again by industrial fabricators, stamped into blanks, or spun into microscopic filaments for circuit boards. How does a molecular marker possibly survive being repeatedly liquefied at extreme temperatures?
It survives because the marker isn't an external label or a superficial stamp. It is fundamentally integrated into the atomic lattice of the metal itself. They utilize highly specialized dopants or unique isotopic signatures that share the exact high-temperature resilience of the host silver. Because these specific molecular markers do not burn off or degrade during the extreme thermal stress of smelting, the unique physical barcode remains entirely intact regardless of how violently the metal is reshaped.
So an auditor or a supply chain manager at a major tech company can take a finished, microprinted circuit board, scan it with specialized equipment, read the invisible molecular signature embedded in the silver traces, and instantly verify that exact batch of metal on an immutable blockchain ledger.
Exactly. They can trace the origin of those specific atoms directly back to the very mine they were extracted from, definitively proving that the material was sourced ethically and sustainably and in full compliance with global ESG standards. It guarantees absolute, unforgeable transparency in a market that is increasingly desperate for verified physical supply.
If we step back and look at the sheer scope of what we've unpacked over the last hour, it completely upends the traditional understanding of what silver actually is.
It absolutely does. If we connect this to the bigger picture, we are observing an element that has undergone a profound evolution. It has transitioned from being a simple, shiny stool of historical value, a passive currency held in ancient vaults, to becoming the absolute, hyperactive, critical choke point of modern industrial and technological progress.
So what does this all mean for you, the listener? We started this journey looking at the ancient world, examining argentum, a metal so inherently soft and malleable that you can barely fashion a functional tool out of it without adding copper to reinforce its structure. We explored the deep quantum mechanics of its krypton core, revealing how a single, isolated, free-flowing 5s electron fundamentally makes it the greatest conductor in the known universe, the exact property that is flawlessly powering the screen you are looking at right this very second.
We examine how that precise atomic architecture is actively deployed to prevent massive lithium-ion batteries from fracturing, how it provides the unwavering electrical baseline for $2 biosensors capable of revolutionizing global mental health diagnostics, and how it serves as the irreplaceable thermal backbone preventing the world's most advanced AI data centers from catastrophically overheating.
We also confronted the stark, unforgiving math of the current market. We are aggressively marching toward a global green transition, mandating the construction of billions of high-efficiency solar panels and millions of advanced electric vehicles. Yet, we are relying on an inelastic supply chain trapped by the byproduct dynamics of copper and zinc that is actively bleeding through above-ground stockpiles, operating in a massive multi-year deficit while the price explodes past historic thresholds.
It is a remarkable, deeply complex narrative of human ingenuity colliding with geological limits.
And as a quick aside, if you want to celebrate this incredible element, make sure you mark your calendars. April 7th is officially recognized as International Silver Day. And if you are wondering about the logic behind that specific date, well, April is the fourth month of the year, 47. It is a perfect, subtle nod to silver's absolute position on the periodic table, atomic number 47.
A very fitting numerical tribute to a genuinely remarkable and vital piece of the universe.
It really is. We have covered a massive expanse of ground today, pulling data from historical archives, advanced university chemistry labs, industrial sector forecasts, and live market economics. Thank you so much for joining us on this custom deep dive. We absolutely love dissecting these complex topics for you and fundamentally changing the way you view the physical world around you. But before we sign off, we want to leave you with one final, deeply provocative thought to mull over. If our required transition to a green, AI-driven future mandates the construction of solar panels and electric vehicles that could mathematically consume up to 98% of all currently known, available global silver reserves by the year 2050, and 72% of our entire mining capacity remains entirely trapped, permanently dependent on the completely unrelated demand for base metals like zinc and lead will, the ultimate bottleneck for human technological salvation be the sheer physical scarcity of the very metal our ancestors spent thousands of years burying in bank vaults as simple pocket change. Think about that the next time you hold a piece of silver in your hand. Thanks for listening.